Hello there, and welcome to this edition of Calculus. So today's lesson, I do like to be upfront and honest with students. This lesson is not very exciting, but it is necessary in terms of derivative and integral rules that you'll just kind of have to know and memorize. And I'm not a big fan of that kind of math, but that sometimes it just is what it is. So. We've talked about how to differentiate e to the x. The derivative of e to the x is e to the x, and the integral of e to the x is e to the x plus c. Well, now this lesson, about a couple different things, but we are going to differentiate and integrate exponential functions other than base e. So, we might differentiate 7 to the x instead of e to the x, or integrate 2 to the x instead of e to the x. And the first thing I'm going to show you is where this derivative rule comes from. And so here's where it comes from. There's this process that a lot of times in math, it's not used too much in AP Calculus, but as you go on in higher levels of math, there's this differentiation process called logarithmic differentiation. Logs and exponents work really nice together. And so let me just show this process to you. So if I want to find the derivative of 7 to the x, then here's what we're going to do. We are going to take the natural log of both sides of this equation. So I would have the natural log of y equals natural log of 7 to the x. And now that I have this exponent inside the natural log, I can move the x out in front. So all I'm doing is rewriting this equation. I haven't done anything with derivatives yet, but all I've done is rewrite the equation in a different form, because that takes care of the exponent. And now I can go ahead and differentiate both sides of this equation. I'm going to differentiate with respect to x. So when I differentiate the natural log of y with respect to x, well, the natural log of y is 1 over y. But remember implicit differentiation. It's been a while since we've done that, but anytime you differentiate a y term with respect to x, you differentiate it, and then you put dy dx. So that's the left side. The right side, well, now we're just differentiating x times the natural log of 7. And this sometimes throws students off, but remember if I said to differentiate 3x, the derivative is 3, it's just the constant? Well, natural log of 7 is just a number, it's just a constant. So when I differentiate natural log of 7 times x, it's just natural log of 7. Well, we're trying to find dy dx, so now I can multiply both sides by y. Running out of room. Should have given myself more space. We're almost there. I want my equation to be in terms of x. So I need to replace y. Well, if you look back at the beginning, y equals 7 to the x. That means my derivative is 7 to the x, because that's what y is, times natural log of 7. So that would be the derivative of 7 to the x. The derivative of 7 to the x is 7 to the x times natural log of 7. So you could go through that process anytime you're dealing with exponents. This is a process that is available to you, but this is also a rule we can just memorize. If we are taking the derivative of an exponential function, then it is the exponential function itself. Just like the derivative of e to the x is e to the x, the derivative of a to the x is a to the x, and then we have to multiply by natural log of the base, which is what happened here. We multiplied by the natural log of 7. And you're really doing that even when you do e to the x. If you would find the derivative of e to the x, well, it's e to the x times natural log of e, which is just 1. And so that's why we get back to here. So you are using this rule even with e. It just so happens that natural log of e is 1. We can also differentiate if a, or that constant, is being raised to some function of x. We just have to do chain rule. So the derivative of a to the u is a to the u times natural log of a, same rule. But then we would have to multiply by the derivative of that exponent, chain rule, so times u prime. So that's how we differentiate bases other than e. It's just the same as the original function times natural log of the base. We can also integrate exponential functions other than base e. It's pretty much the same rule. So the integral of a to the x is going to be, this is your rule, a to the x, but instead of multiplying by natural log of the base, we are going to divide by the natural log of the base. And then plus c. So that's our integral rule with functions other than e. So if I want to integrate 2 to the x with respect to x, well, it's going to be 2 to the x divided by natural log of 2 plus c. These problems, and I'm going to be honest with this entire section here, if you see one of these problems show up on the AP test, there might be one, there might be none. I would be shocked if you would see 2 problems from this entire note outline on the AP test. So I have seen them show up. They are very rare. They don't like to test memorization per se. They like to test conceptual understanding, but they can show up. So I do think it's my responsibility to make sure I show them, even if they don't show up very often. Well, we can integrate 2 to the sine of x cosine of x. And that looks really, really messy. It looks a lot tougher than 2 to the x until we remember we have u substitution in our back pocket. Remember I said try to find u to be something where the derivative of it shows up elsewhere. So like if I have sine of x be my u, the derivative of sine of x shows up right here. So u being sine of x is going to be a really good candidate. So u equals sine of x. Du equals cosine of x dx, which is what we're trying to replace right here. So that's our du now. So now we have the integral of 2 to the u du. And we are essentially in the same exact place as we were in the previous problem. So now the integral of this is going to be 2 to the u divided by natural log of 2 plus c, and then replace the u. So 2 to the sine of x divided by natural log of 2 plus c. Fun stuff. Okay. The next thing we're going to talk about, a little bit different. That was exponential functions other than base e. And I've kind of alluded to this throughout the year, how there are these other rules. I've given you this pink sheet. There are these other rules that we're going to have to know. We're going to have to know all the derivatives of the inverse trig functions. And they look really messy. They look really sloppy. We're also going to have to know these 3 integral rules, which are on these notes down here at the bottom. These 3 down here. So I'll talk a little bit about those as well. So again, these are just rules that we're going to have to memorize and know. I will say this. On this lesson video, am not going to get into the why on this, just mainly because of time. But if you are interested, I do have a video on my Canvas page as well where you could watch it. It's a different teacher, but explaining where these derivative rules come from, which could be a really good video to watch. It could help in terms of, maybe you don't have to memorize them, but if it does pop up, if it does happen to show up, then you have a way to find the derivative rule. Is it the way I would go about it? No, I don't mind memorizing things, so I would probably just, spend some time memorizing these. I would also encourage you to write these out. I'm reading a book right now. It's a fiction book, mystery book, and the main character is taking a bunch of notes by hand. He's interviewing someone, and the girl says, wouldn't it be quicker just to type everything? And he makes a statement where when you write the words, you own the words. And I actually just read that yesterday, and I thought that was really powerful. The more you write things, the more it sticks with you. So rather than just looking at these, I would write it out several times. But this is how you find the derivative of arcsine, which is the same as sine inverse, tangent inverse, secant inverse, cosine inverse. And you can see they're basically the same rules on the left and on the right. Kind of like when we differentiated, secant and cosecant and tangent and cotangent. They were basically the same rules, but became negative and the reciprocal functions. Similar idea. It's the same exact thing, but all of the c functions, arc cosine, arc cotangent, arc cosecant, they're just all negative. So if you just remember one side, then the other ones are all negative. So it looks like you have 6 to memorize. You really only have 3. Okay, so I'll do one example here. If I want to find the derivative of arcsine of 2x, well, to use the formula, here's our formula, we really just need to know two things. We need to know what u is, and we need to know what u prime is. That's how we start these. We have to identify the u, right here, this thing here, and then we also have to identify u prime. Once we know u and u prime, we just plug them into the formula. So the derivative of arcsine of 2x, well, our u is 2x. So our u prime is 2. And once you know u and u prime, just plug them into the derivative formula. So it's going to be u prime on top, so 2, over the square root of 1 minus u squared. U is 2x. So quantity 2x squared. If this is a free response question, you can leave that. My guess is they would square the 2x, just a hunch. So 1 minus 4x squared. That's our derivative. Again, are these likely to show up on the AP test? Not likely. You know, we'll have a chapter test where I'll definitely make sure you know these, but it is what it is. And then there are 3 integral rules that we'll have to know. Now, the grossest one looks like that bottom one. What I've been told is on the AP test, they're much more likely only to focus on the first 2, if at all. I've never seen a problem with this bottom one down here. I've never seen it. I have seen arctangent a couple of times. This is the one that I have noticed is the one that shows up if any inverse trig does show up. It's this one. So we'll do an example of that, and we'll do an example of arcsine. So again, I would write these out just to get in a habit of them. Okay, so I have this integral right here, and we really just need to kind of match up the form to first identify, am I dealing with arcsine, arctangent, arcsecant? But it's you know, now that you know u substitution, it's easy to look at this and try to have this be u. I have a lot of students that will say, okay, let's have 16 minus x squared be u. Let's try that to be u and do u substitution. Well, then the derivative is negative 2x, and there is no other x term anywhere. So u substitution doesn't work on this. Same thing down here on example 5. You know, students will look at this and say, okay, if I have this whole denominator be u, well, then the derivative is 2x, and there is no x term. U substitution doesn't work. Here's where you need to be careful. If I made this example of x over 25 plus x squared dx, this is a completely different problem than this one is right here. Because this one, I can use u substitution. I would have the denominator be u, and then I can do a replacement, and I wouldn't have to do any of this inverse trig stuff. So you need to be very careful with fractions when you're integrating. And we're also going to have, second semester, another integration technique to integrate fractions called partial fractions. So when you're integrating fractions, it's not always straightforward. You need to be very careful. Okay, so here's our process. I made some pretty basic ones because if these do show up, they're not going to try to challenge you with these skills. They're just going to want to see if you know the skill. So I made some pretty basic ones. So here's how we go about this. So a is our constant, like the a squared is our number. So our a squared is 16. And our u is always a function of x. So our u squared is the x squared down here. So I'm going to start by identifying my u squared and my a squared to match up the form here. I'm trying to get this form to match this form here. So my u squared is x squared. My a squared is 16. So I'm trying to match the forms between these two things. Okay, well that means that u equals x. Because if you look here in the formula, I'm trying to figure out what u is. So u is x. I know I'm going to have x right there. My du is the same now as dx. du equals dx. We're basically doing a form of u substitution. We're just not having the entire denominator or even the entire integrand be u. Just u is that x right there. So we are doing a form of u substitution. Our a is 4. And so now I can associate this thing right here with the integral of du, because dx is du, over the square root of a squared, because 16 is a squared, minus u squared, because x squared is u squared. And I basically now have the same exact form as what this looks like right here. So I can integrate this. This is going to be arc sine of u over a, so x over 4, plus c. Now this is one where there's not a lot of different u substitution going on. You can match up the form pretty quickly. Is all of this stuff over here necessary for this problem? Probably not. But I wanted to show it, in case it said minus, 4x all squared, then we would have to identify u, and it would be a little tougher. But my guess is if you see one, it's going to be pretty much like this. The one I've seen most often is this form right here. This is the one we need to be most aware of. This is arctangent. Okay, so we're going to go through the same process. I try to match up the form. I see, okay, it looks like this form right here, pretty much the same. So I know I'm dealing with arctangent. So I'm going to go through the same process as I did before. I identify my u squared. U squared is x squared. A squared is 25. So u equals x. So du equals dx. And a equals 5. So I could rewrite this to match up this form up above. This would be the integral of du over, and then it's going to be a squared plus u squared, which is the exact same form as what I have up above. So now I can use this direct formula right here. Like I said, these are as basic as I can make these. And that's why it doesn't look like there's anything weird going on. It looks like, why are we even going through this whole process? Well, like I said, sometimes u squared isn't just going to be x squared. So we need to be careful there. So our form is going to be 1 over a, so 1 over 5 out in front. And then it's arctan of u over a, so x over 5, plus c. So not the most exciting stuff, I'm well aware of that, but it is my responsibility to teach it, and so I wanted to make sure I did. How much time you spend, memorizing these is up to you. There's always a trade-off in the amount of time you spend working on something. When would it be worthwhile working on something else? That's up to you to decide, But these are rules that, according to College Board, you guys do have to know and can be assessed on. Is it a lot? No, there might be one question. But that is our lesson. Have a great day.